Welcome to a lesson with Dr. Powell. Let's take a look at an optimization problem in calculus. All right, we're going to be trying to minimize something. We want to minimize the time it'll take to move across, let's suppose this is a river or something, a river from point A to point B. If we can move twice as fast, exactly twice as fast, this is a little contrived, twice as fast on land as we do on water. And we know maybe it's 1 unit across, maybe kilometer or something, and 3 kilometers this way, or however we want to think about it like that. The question is, what angle should we do to minimize our time to go from A to B? Okay, so we want to minimize time, so we need to have a formula for time based upon theta. All right, so let's think about this for a minute. T of theta is equal to, let's think about the time it takes across in the water right here. First, how long is it that we're traveling in terms of theta, if this is a 1 right here? When we think about our triangles, how we define our trigonometric functions with a 1 here and a theta here, this side length would naturally would just be cosecant theta. So if that length is, so that's distance from here to here. Okay, now our speed, I didn't tell you what our speed is, but maybe perhaps it'll cancel out somewhere. So let's just kind of make a statement. Let's suppose that our speed in the water is v. So we're moving at speed v. So then our speed on land, it would be 2v. All right. So suppose it's a constant v here and a constant 2v there as we're moving on land. So if we have, how do we get time if we have distance and constant speed? Well, distance is equal to constant speed times time, right? So what we could think of, okay, so distance in general is equal to, if it's a constant speed times time, and which should make sense because the derivative of this would be, because with respect to time, would just be the constant speed. Which is what we wanted it to be. Okay, so distance is equal to constant speed times time. And so how do you find time? By saying distance divided by the constant speed. So distance is cosecant theta. So let's just kind of do that for a second here. And let's come over here and just erase this. Okay. So we get T of theta is equal to distance cosecant theta divided by the constant speed of v. Now, what about on land? Well, let's see. This length, with the 1 being here, this would actually be cotangent theta. So we know cotangent theta to this point, and that's using our triangle with the 1 here, then this side length is cotangent theta, just like that one's cosecant theta. So the length on land, then right here to here, is actually 3 minus cotangent theta. So that's the distance on land divided by the speed, okay, which is 2v. So 3 minus cotangent theta all over 2v. So that's the function for time. When we take a derivative, notice that we could actually factor out a 1 over v out of it all, and this is a constant because of constant speed. So really it won't depend on that. If we factor out the 1 over v, we're left with cosecant theta plus 3 minus cotangent theta all over 2. And that's the function here. This will not matter for the derivative. So let's just ignore it and take the derivative of this part right here. Now, if we want to, if we multiply everything by a positive constant, it's going to be a minimum at the same for the same value of theta. So we could, and that'll eliminate this division by 2 there. So really, let's just look at 2 cosecant theta plus, so multiplying the whole thing by 2, plus 3 minus cotangent theta, and we're going to take a derivative of this now. Taking a derivative of 2 cosecant theta is negative 2 cosecant theta cotangent theta. Derivative 3 is gone here. Negative cotangent, that would be a positive cosecant squared theta. We set this equal to 0. Now, again, I like to convert things to x's and y's. Cosecant is the same thing as, if you think about it in terms of x's and y's, is like it's 1 over sine, so it's 1 over y. So negative 2 times 1 over y times cotangent is x over y. And then over here we get cosecant squared is just 1 over y squared. Okay, so yeah, so taking a look at that, so x over y and 1 over y squared, and adding fractions. So notice we have a common denominator already, y squared and y squared. So it really looks like negative 2x plus 1 all over y squared equal to 0. Numerator fractions equal to 0 when numerator is 0. So really, so x should just be equal, to make this equal to 0, x should be a half. Now remember what x is. X is cosine. Woo! When is the cosine 1/2? So like the x value is like the smaller of the special angles, so it's closer in this way. The pi thirds or 60 degrees say, aha! We know that theta is equal to 60 degrees actually wins here, right? At least that gives us a critical point. Is it a minimum? I guess we could check that with a kind of a second derivative test. I mean, we took a derivative here. In my last video, I gave a description of that in another example. You can look at that. It really is not too bad on how to make sure that you have a positive second derivative, so it's concave up. So it really will represent a minimum. So that'll work there. But at least we found out the angle. The angle is 60 degrees, and that'll minimize the time that it takes in this particular situation. Okay, thanks for watching.